Okay, so any question about the topic today? Yeah.
In one of the video, you are explaining the one operations and then we say that if we have the output that is a number, we like lost information and we cannot present the so it's
One.
I don't think that is not very
Okay. So the question, I will introduce a bit more the question, and then we will discuss about it. Okay, so what is a point transformation? So in general, it is the image, the output image at a given location is a function of the input image at the same location. This is in general. Okay? And this has the structure y equal f of x. So in general, we will talk about y equal f of x. Okay? And this means that if I have an input value, okay, so input value, I have an output value, then there will be some transformation in it. So let's say that I will prove any transformation that is vertical. Okay, so say that we have this transformation that is y, and let's forget for the moment that it is defined between 0 and 5. Okay, so they can take any value. So let's say that y is equal to x. So given x, I can compute y. Given y, can I compute x? You simply have to invert this. So x is equal to y over 2. So yeah, given x, you can given y, you can compute x. And that is a one-to-one transformation. So given any x, there is only one y. Given any y, there is only one x. So these transformations are invertible. They are also one-to-one. And what about the following? So what if I have a transformation that is like this? I have x, I have y, I have this transformation. So now, given a y, I don't know if this was the input x or if this was the input x. So given x, I can compute y. But given y, I cannot compute x. So what this transformation is not invertible. So that means that if you transform an image using this transformation, you have lost information. What about this one? So this is obvious. What about this one? So now we will have x, y. Our transformation is something like this. What about this one? Is it invertible or not? Given y, do you always know x? No. There is a reason. All these y's, I don't know which one of these x's could have generated y. Okay. So if a function is invertible, you will lose information. If a function is not invertible, then you lose information. That was your question, wasn't it? Okay. More questions? No more questions. Then I go to my favorite slides. Let's go to. Okay, so what do we have here? See. This is a kind of transformation that we will be able to do. So this is a original, and then we can do increase brightness, increase contrast. We have multiple operations, and all of them respond to this structure. That is the one that I put in the whiteboard. So you have an input pixel, you transform it, and then you produce the output pixel at that location. And yeah, so if you have a color band, a color image, you can apply the same function to all bands, or different functions to different bands. And what is a lookup table? So lookup table is a table that represents the transformation that you're doing. So when you're this is a general concept with functions. When you write this function, why do we write this function? Why do we write this? Because it is a very convenient way of writing a transformation that is very inconvenient to write. So I could have written this like 0 goes to 0. Sorry. 0.1 goes to 0.2, 0.5 goes to 1, minus 0.5 goes to minus 1, and 1 goes to 2. So I could have written all this table, but this table is infinite. It is so inconvenient to write that it's much simpler to write this thing. So now you have an algebraic relationship between x and y. And given this relationship, you can construct your lookup table. This is your lookup table. So lookup table because when you want to find what is the transformation of a value, so what you look at for that value. So you look at 0.1, and then in the table it will tell you what is the corresponding value. But this y could be completely crazy. We cannot even find what is an algebraic description for these. But as long as a symbol x produces a symbol y, that is a function, that is a constraint to be a function. So every x produces a y. Doesn't matter if you can find an analytical description for that or not. Okay, so this is a function. This is a function. Okay. So single x produces a single y. And if you can find a convenient way of writing that, the better for it. But this is a function. Okay, so look at what is simple. So you can give any function. Maybe sometimes you can find the analytical description of that function. But it doesn't always need to be the case. So, yeah, so this is a lookup table. So sometimes we find an analytical expression for that, like this one. So this is called the sigmoid function. So the sigmoid function has some interesting numbers. So one is this number on top. This number on top defines what is the maximum value of the sigmoid. Another interesting number is this one in the middle. This one in the middle, general in mathematics. Okay, so let's say that you have a function. You have a function that is whatever y is equal to f of x. Let's say it has the same shape as the one, this one that I will change the difference for. Okay, so y is equal to f of x. Say is this one. But now I construct a different function. This is y1. Now I construct a different function that is y2 is equal to x minus x naught. What will happen? What will happen? How will y2 look like? Shift to the left or right. Let's say that x naught is positive. To the right. Okay, so if we go like this, it will be the same function, but now it is shifted to x naught. So whatever before happened at 0, so whatever happened at 0, now it is happening at x naught. So this is actually what we have done here. You see, it has the same structure. So x minus something. So that means that originally, if we don't put the 127, this would be shifted to 0. So this would happen at 0. But now, because we have shifted it to the right, this happening 127. And then the other interesting number is this a divided by 32. So actually, it doesn't matter if it is 32 or whatever. So what is the coefficient in front of this? And this coefficient determines the slope. Okay, so you can go faster or slower between these two extremes. So you may go, so let's say what we have here. I will not shift it now. So you can go like this. You can go much slower. You can go much slower. Okay, so the asymptotes are the same, but we go faster or slower. Okay, so this is controlled by the coefficient in front. Okay, good. So then, this is simply that you can apply transformation to each one of the bands. So we can apply this transformation to any input image. So given any image, you can take whatever value is here, you do it for the 3 bands. So now you have a single value. I come to here, and then I substitute what is this value? It is 127. I come to here, and then I substitute by whatever this function tells me. Yeah, so some examples. Let's say that I apply this transformation. So this transformation to each one of the bands. So let's start with something easy. So the red band. So the red band, I will saturate the small values. I will saturate the high values. So how was the red band before? The red band before was like this. So all the dark areas, I will make them darker. All the bright areas, I will make them even brighter. Okay? All these dark areas, now they are darker. And all the bright areas, they are even brighter. Okay. And then, yeah, I'll come back to that later. Okay, so what about the green one? So the green one, what is that? How would you describe that function? It's an inversion. Okay, so what is that function? Function is y is equal to 155 minus x. So this minus is an inversion. It is changing the contrast. So whatever was black now will be white. Whatever was white now will be black. And all the gray values in between. So now we look at whatever was black now should become bright. Right? And whatever was white is standard there. Now, black. And what about this one? This one is keeping more or less, keeping the contrast. So if something was dark, it will stay dark, it will be darker. So 25 is substituted by 50, so it will be a little bit brighter. But that is true up to 127, and then there is an inversion. So the background should become brighter. That is what's happening. See, the background that is in this area, background is in this area. So this is brighter. And then the thunder that was bright. So thunder was here. Now it is inverted. And now you have transformed the three channels, and then you combine them back for colors. Yeah.
How do you know that background is?
Because the background, see? If it is dark, it has to be in the left. It has to have low values. Right? Okay. So now we can transform this image, this one. So is the information content the same? Have we lost anything? And we recover the original image from this one? Do you think? Why not? Yeah. So the blue transformation is not inverted. So given this value, I don't know if it was produced by this one or by this one, so it is not invertible. I have lost information. And it is the only one that is missing information, is losing information. Which other one? Red. Why? So all these saturated values, they are also losing information. Okay, so then what transformations can we do? So we can shift all the values up. So this line is y equal x, so that is no transformation. And then we can add the number. And we have to be careful. We have to be careful because if our images are represented between 0 and 55, and then you have 255, and you add any number, positive number, then will be above 256. So you are saturated. So you have to saturate here. So, but yeah. So here in the histogram, so you can see how the histogram looked like before. So the histogram, this was the histogram of the luminance. We already know what the luminance is. So this is the histogram of the luminance. You add a gray value to the luminance, then the luminance becomes saturated. And brighter, because we have increased the brightness, we have increased the luminance. Okay, and decrease the brightness, then we have to saturate on the lower side, and you do it by subtracting value. And we can decrease the contrast. So we can, so let's look at what this function is. So let's see. I'll write it here. So that transformation was written like this. It was x plus s as s. Okay, so actually I can take this x, put it on the left. I can write it like this. I can write it there. And in general, it has this form, y minus y naught is equal to a function of x minus x naught. Only that x naught and y naught in this case are the same. So what does it mean? So we already know this trick of shifting the x, but now we have a new trick that is the same, but now in y. So that means that we may have, let's say that this is our blue function. We have a function that is y is equal to f of x, whatever that function is. I always draw this kind of function because it is it's convenient. So this is this function. But now, if I have this function, this one here, which one? So let's say that this is y2, this is y1. So where is y2? So y2 is the same function. It's the same function. But now it has shifted this point here, response this point here. So 0, 0 has moved, 0, 0 has moved x, not y. So it is like making a change of coordinates. See? So it is like now we are in a new coordinate system, x prime, y prime. This is x prime. This is y prime. So this kind of fractions we are doing is shifting, defining a new coordinate system. And so in the new coordinate system, the function, this new coordinate system, function looks like very simple one. Okay, so now let's look at again at our transformation. Our transformation was this one. So that means I'm shifting my coordinate system to the point SS. And then my transformation is very simple. My transformation, let's make it red. So my transformation is this one. In the new coordinate system. Okay, so yeah, that's what's happening. So let's say that S is 127. Then this structure is simply A times the input. So, and A is between 0 and 1. So that means that that is a straight line that goes to the point 127, 127, and it has a slope that is smaller than 1. It's between 0 and 1. And then what will happen? So all the values that are between 0 and 255 will be mapped onto a region that is smaller than between 0 and 255. See, so this dynamic range is smaller than the original. So we have compressed the gray values in all bands. Let's look at the original. So the original looked like this. So we were not using the beginning, we were not using the very end, but otherwise we were using a lot of gray values. But after transforming, we are using very few. So what we are doing is decreasing the contrast. So contrast actually is the difference between the minimum and maximum value. It is the difference between this minimum and this maximum. But is the contrast. And we can do that. We can decrease the contrast with a slope that is smaller than 1 but we can also increase the contrast. So if I make now, this is the same transformation, but now A will be darker than 1. So now, instead of having a very small slope, we will have a much larger slope. We have to be careful with the saturation. Okay, so saturate appropriately. So you see there the histogram at some points have been saturated. And then you are increasing the slope disabled. Okay, good. Then increasing the contrast is putting a slope that is larger than 1, decreasing the contrast is putting a slope that is smaller than 1. So, and you can shift it if you want. So, for instance, let's say this is a very typical transformation. And let's go here. Let's say that I have an image. This is my L. I have an image whose histogram is defined between the minimum and maximum value. This is the minimum of x. This is the minimum of x, the maximum of x. And then I want to map it onto another line that onto a range that has a minimum of y and maximum of y. So what is the equation of this transformation? So my input is defined here. I want the input to be defined there. Okay, so what is the equation that goes this? So it's y times y. And you recognize here is y minus y naught. See? So you recognize here that we have shifted our coordinate system here. Okay, we are shifting. This is x prime, y prime, and this is y prime. And then we have to put the slope. So the slope is ny minus ny. Divided by x minus x. Then we have to x minus x. And again, we recognize here this is x prime. But this is structure of x minus x naught. So actually, this x prime, y prime are a new coordinate system centered at that point. And now we have a single coefficient in front. This is our A. But it has the same structure as y prime is equal to A x prime. Okay, so a convenient, so typically you want to map the minimum and maximum values onto 0 to 55. So the most common way that you see this is like this. So then the minimum of y is 0. So I have to write it. And then the maximum is 255. And then divide by whatever you have in the input. So this is a typical way of writing, but this is a more general one. So you can bring it from whatever you have, to whatever you want. All computers, all displays, they always do this transformation. So they typically take an image and they map it before displaying. They map it to 0 to 55, just to take advantage of the whole intensity range. Okay, so now so these histograms, it is how there is something interesting that let's say that we have values, x values we will do two transformations. One will be 0.5 x. The other one will be 2x. So let's concentrate on the middle of the table. So let's say that we have the value 128. So the value 128, according to this transformation, will be transformed into 64. And according to this transformation, let's forget for the moment that we are limited to 255. So this one, according to this transformation, will transform there, and this one will be transformed there. What about the previous one, 127? So when you multiply by this, let's say that we always want integer numbers. So this will be mapped to 63. This will be mapped to 254. And what about the next one? This will be mapped to 64. And this will be mapped to 158. So we notice a few things. So the first thing we note is that there are numbers that are repeating. So there are two numbers that are mapped onto the same gray value. And that happens when your coefficient is more than 1. The other thing we note is that there are gaps. 257 is never reaching here. And what else? So something else is that here there are no gaps. Here there are no gaps. So all values can be reaching from the input. So that should translate in the histogram into some distinctive features. Probably you see in your computers, but you probably don't see it from the distance, but you see bars here. So we see a kind of continuous histogram here. Now it is not continuous anymore. Why? Because we have zeros in between. So we have a value, then a zero, a value, then a zero, a value, then a zero. That is what's happening here. Reach 257 in my histogram, 257 will get a zero. So there are values. When you're increasing your contrast, there are values that cannot be reached. Okay, then also okay, good. Then what about this one? So we can construct a transformation that looks like this. So this is called the gamma transformation, and all monitors apply these gamma corrections of this gamma transformation. So gamma transformation, depending on what is the value of gamma, for instance, for gamma larger than 1, it looks like this. So is it increasing the contrast or decreasing the contrast? Increasing. Everyone agrees? I partly agree. So it is increasing here. Here the slope is larger than 1, but here the slope is smaller than 1. So it is increasing the contrast in the low values, the dark areas, and it is decreasing the contrast in the bright values. Now this is the opposite. So it is decreasing the contrast in the dark values and increasing the contrast in the high values. Now we see these spikes. Where are these spikes are coming from? So this is the histogram, and we see holes. Okay, now the holes we understand where they're coming from. So they are coming from values that are never reached from the input. But what about the spikes? What spikes are also there. These two, 64 now, the histogram in the output, will get the count from 128 and the count from 129. So these two will collapse onto the same output value, and it is causing these spikes. How often they happen? So this is caused by rounding, right? So every time that you have to round and at the end you are rounding to the same integer value, then you're getting these spikes. So reminder, so we saw this yesterday. What is the PDF? What is the CDF? Any questions so far? No? Then, what if we use, so you have watched the videos. So what is histogram equalization? How would you describe histogram equalization? You have seen the theory before. So it is a transformation such that we try to make the histogram of the output as equal as possible. So that is why it is called histogram equalization. Okay, so now, what is my transformation? So I can compute this PDF, right? So I can compute the histogram of the input. I can compute the cumulative density function. And the cumulative will go between 0 and 250 and 1. But why not making it go from 0 to 255? So I can think of this as a function and as a lookup table. Then I can simply multiply this by 255 so that now for any input value I substitute by something that will go from 0 to 255. And where am I increasing the fruit? So interesting features here. So the minimum value here, let's say it is 30. So 30 will be mapped to 0. This is the same as what we were having here. So this is the same as with this transformation. The minimum is transformed onto the minimum of y. So 30 is transformed to 0. So it has an interesting property. We will take advantage of all the output of all the dynamic range the output. What other features do we have? So we have here, it is the slope larger or smaller than 1? Larger than 1. So here we are increasing the contrast. Here we are decreasing the contrast. Okay, but in which area we are increasing the contrast? We are increasing the contrast in the area where we have a lot of pixels. And we are decreasing the contrast in the area where we don't have so many pixels. So if you don't have pixels with these values, I don't mind sacrificing contrast there. If I have a lot of values here, this is where I want to have the contrast, because this is where my information is. I don't have any information here, and I have 0 information there. So I don't mind sacrificing the contrast here. I don't mind sacrificing, it is a little bit of sacrifice, but I have so few pixels over there that I don't mind sacrificing the contrast. But I want to increase the contrast where I have my pixels. So now you can transform, so you can use that function as the transformation. So transformation here. So now my transformation, instead of this one, will be this one. So y will be 255 times the CDF of x. So if well, this would be my histogram equalization. It is written a little bit, but it is because okay, here we have the coordinates, we have the bands. This +1 is coming from MATLAB, because MATLAB, the zero index doesn't exist. So the all indexes in MATLAB start at 1, but this is the formula that so. Okay, good. Then, yeah. So this is and once so here you recognize the same. This is the mapping, remapping between minimum and maximum. You recognize it. So it has maximum value, minimum value, maximum value, minimum value. This is the slope. So it's the same. But this is just a remapping. Okay, so now this is, let's say that we do it with the value image. This is the histogram of the value. This is the CDF of the value. So the cumulative density function of the value. And we use it to remap. So wherever we have a lot of pixels here, in the middle range, we will increase the contrast. This image has much more contrast than this one. You may like it or not, but it has more contrast. And so this is our lookup table. So simply taking the CDF and multiplying by 255. This is the same. Yeah, so here, I think here it is very nicely illustrated the decrease of contrast. So all this area, the slope is very small. So that means that bands in these pixel values, they are mapped to very similar values in the output. While bands in this area, they are mapped onto larger. So let's say that we have a band of 10 pixels here. So 10 gray values. So these 10 gray values are mapped onto 12 gray values. We have increased a little bit the contrast in that area. While here we have 10 gray values, but then they are mapped onto just 1 or 2 gray values. Okay, so now this is the histogram of the luminance after equalization and so on. So yeah, this is interesting. So we are trying to make it as uniform as possible. Do we succeed? No. It is much more uniform than this was. So this was not uniform at all. Now it is a bit more uniform, but it is not completely flat. So a uniform distribution is flat distribution. So this is not flat. We have holes, we have these spikes, see spikes there. So and we understand where the spikes are coming from. They're coming from rounding, and then the holes, they are also coming from rounding. And yeah, so we can actually do it in a so you can apply this histogram equalization to the value, to the luminance, to each one of the bands. Let's do it for the luminance. So we do it for the luminance. This is the luminance CDF. This is the lookup table. This is the equalized. So we can compare the luminance image with the equalized luminance. And this is very interesting. You can learn the function in one space. So the space, oh, sorry, it is 22. Well, let's make a break. Okay, so we were here. So we were saying, okay, so I can learn the transformation in one of the spaces. So I can learn the transformation in the luminance space, and then I can apply it to any other space. So I can apply, for instance, I can compute the color histograms, I can compute the CDFs of the colors, and then I can apply to each one of the colors, but I can also apply the luminance CDF to all the color bands. And then this is the one that I will use. And now this is the color bands now corrected according to the CDF of the luminance. So let's try to write that. So here I didn't specify the CDF of whom, but we can say the red color at a given point. Let's make it bigger. Sorry. Let's make it bigger. So much. So that I write at the same size. So the red color will be 255, the CDF of the luminance by the red. So this is the red in, this is the red out. And you can also do it according to its sound, CDF. So you can be very creative about how you transform your images. So you can use the CDF of the red channel, or you can use the CDF of the luminance channel and apply it to the red to the red channel. So you can be really, really creative. And what happens is that here, this is not one. This is what I want. That this one has a much more natural appearance than this one. Yeah. So this is applying the CDF of each one of the bands independently, and it is somehow changing the colors. You see, it has more contrast. All of them have more contrast, but this one is changing the colors independently. So each color is transformed according to this function. So they are more or less all of them the same. So all of them share this empty area. All of them share that they have a smaller slope here, a larger slope there. But the specific details are not exactly the same. So that's why the color relationships, they are slightly changed, and these colors are much more unnatural. But if we apply the same transformation to all of them, so we apply this one to all of them, again, we have gained contrast, and now the color relationships are much better preserved. So you see it here. And you have much more contrast. You see the forest in the background, you see much better the differences between minimum and maximum values over there. Okay, so there is another application that is very interesting, that is histogram matching. So why we want this? I will do it here. This is the one I want. Okay, so let's say that you have a couple of images from kind of similar areas. So you have a picture of a garden like this. You have another picture of the same garden, but different regions of the garden, and looks like this. So the camera here was miscalibrated. So somehow the colors here, they are too saturated. You see that the green is too much green. This green is unnatural. So it is a problem of the camera. So can I change these colors according to these ones? So that I transform that, this was the original situation, into that. You see, this is what I want to achieve. So I want to change the camera, a picture whose colors have been degraded by this one, whose colors are much more natural. And the same can be applied to, you have a couple of cameras pointing to the same, all object, and then you have different color calibrations, and then you want to make both of them to have the same calibration. So this is this histogram matching. Okay, so to do so, we will have now a couple of images. Let me go to the beginning. So I want to remap an image I so that it has a histogram that is as similar as possible as the histogram of another image J. Okay, so let's see how we can do that. So let's say that we have the cumulative density function of the image I and the image J. And just to keep things simple, we will only consider the gray values between 0 and 15, not 0 to 55. Those are too many. Okay, so let's say that this is the CDF of I, this is the CDF of J. And I want to find transformation. So I want to find this transformation. So I want to find something that given a gray value in the input image gives me what is the gray value, not in J. Actually, this is not correct. So I want to find an output for the image I, but it has to be such that the histogram of this, so this histogram, the histogram of GI out is approximately the histogram of GJ. So I want to find this transformation here. How do I do it? Okay, so let's go back to the CDF again. So let's say I want to transform the 5 into something. So this is the left value in my column. So I have this table. So this is 5 on the left. I have to find what is the corresponding value in the output. Okay, so if I look at the CDF, I can look what is the CDF of 5. So what is the CDF of 5? So I have 5 here. So this is 5. What is the CDF of 5? So the CDF of 5, the CDF in the input image I of 5 is equal to the probability of a pixel from the input image I being smaller or equal to 5. This is the definition of CDF. Then, this is the value. In this particular case, that value, let's say, is 0.65, let's say. So this is 0.65. 0.65. Then I can wonder, okay, what is the CDF? What is the value? So I have to find the value in the image J. Now I will use a different color. So I have to find an X such that the probability of J being smaller than that value is also 0.65. But if I find that value, my transformation will be 5, I will transform it into X. So if this is, this is the CDF of 5, is the probability of I being smaller than 0.5 being, so the probability of I being smaller than 5. Okay, so I have now to solve for X. So I can write this equation here. I can write it in this way. So this is the CDF J minus 1, 0.65. It is look for a value X such that the probability of being smaller than that value is 0.65. And I will call that CDF minus 1J. So the value that I have to put there, so for any given value X, so for any input value X, this. So this value here is the CDF minus 1J. This minus 1 means the inverse, but the inverse in the sense of functions, not in the sense of numbers. Or, and now we change now, the CDF I of X. So this is 0.65. And this one, now we look for, I will never find exactly 0.65. So I have to find one such that 0.65 is between the CDF of that value and the CDF of the next one. So that I will substitute by 10. So why 10? Because this being smaller than 10, it's, let's say, 0.67. Being smaller than 9 is 0.60. So 65 is between 60 and 67. So I will take 10. Okay. So you will never find the same value. But the idea is you try to find the best matching value. So this 10 is 10. All these is 10. So you will substitute 5. Substitute 5 by 10. And you do the same for the back. Okay. So I can do that. So once you find these correspondences, this one here. So for every value in the input image, this is what I want to get. This is J. So, and this is my lookup table. So I have to find for every value what is the CDF of that value, the original image. I have to find a value in the output such that the CDF is between two bars. Okay, so therefore I will substitute by 10. 4 I will substitute by 10. 5 I will substitute by 10. 6 I will substitute by 11. So on. So this is my lookup table. And when you apply that, do I exactly get what so I wanted this histogram to be as similar as possible to this one. Did I completely succeed? It is more similar, but it is not exactly the same. Okay? And this is a general result of histogram equalization, histogram match. So it is much better than, or it is much more similar than the original, but it is not exactly the same. So here you have, for instance, let's say that I have this image. This is the kind of histogram that we want to have. So in general, this image is darker than this one. So if I remap this histogram to look like this one, the image should become brighter. That is what happens. And you can do it also. These are same examples. See them by yourselves. So I don't think the time to get it. If you have a question, feel free to ask. So so this one is interesting. So this is the PDF of. So let's say that we want to remap. This is my original image. This is my target image. So this is I, this is J, and I want this histogram to look like this one. So this is the result. So this is a bit. So this is a little bit blue. This is a little bit more red. So this one should become a little bit more reddish. It is what it does. And here you have all the lookup tables and all of these things. So you have the PDF of the green, this is the rocket, this is the PDF, the rocket again, so red, green, and blue. And then you have the PDF of this cartoon. So you have the PDF of the cartoon, this one and this one. And how can you look at, so how do you know this image is more reddish than this one? And I see that in the histogram. Which of the two has more red content? How do I know? Where are the red values of this image? They're here. This is where you have the rise. So here you have very few values. It's almost flat, the CDA. So all red values are almost here. While these ones, they are much more spread. See, we are occupying all this area. We have many more red bright values and many more in this middle area. So this image is more red than this one. You can see that from the histogram. And then this is the lookup table. So this is this process that we have done of finding the best matching CDF. And then this is how, after applying the lookup table, how it looks like. This is transformed into this one, and this is transformed into this one. This is not exactly the same as the one that we wanted, but it is much more similar. And then using that, you can make these corrections. Corrections, and here you have the whole description, and at the end, you have lookup tables. Like this, you can go from a degraded image to an undegraded image. Here, you have the lookup tables. So the lookup tables are these ones. That's it. Any question? No questions. Let's look at an iPhone. Let's go to iPhone. This time I have chosen this paper here. This paper here, simulated exposure fusion, but the name may not mean much to you. But when you read the article, the abstract, you see simulated exposure fusion is a single image contrast enhancement method. This is what we have been doing. So we have a single image and we are doing contrast enhancement. This is our stuff. Okay, so we go to archive, and there is an example I particularly like. I like this example here. So look at the original image. Can you see anything? Yes. A little bit, but because you are in the first row. You see a little bit, but not so much. So it is a kind of very easy image. But now you apply this. Of course, you don't get a perfect image, but you see much more than you saw at the beginning. And how do I do that? I have to apply some transformation. These are my remapping functions. So you would have to read the paper to understand what this K is. So there's a factor in the algorithm that is a parameter K, but you try to understand what it is doing somehow. So it is taking values and gray values in the input, and it is applying this kind of functions to the input, and then it will create from a single image, it will create 4 outputs. So now it's doing something like this. So always think in terms of systems. Okay, so you have an input image. So you have an input image. Now you apply 4 different systems. So 1 with k equal -1. Make sure that I get the right. So you have a system with k -1, another system with k equals 0, another system with k equals 1, and another system with k equals 2. And these are, point processes that we have studied today. So how did they come to these transformations? You have to look at the reasoning in the paper, but they will follow similar kind of reasonings to the ones we have used today. And then you take all these and somehow you have to combine. So a very simple combination doesn't mean that this is the one that they are doing. Okay, but a very simple combination would be adding all of them. Okay, and doesn't mean that it is the one that they are doing. And in general, they will put another system. Sorry, they will put another system here that applies a combination of them and produces a single output. I out. But the result is really impressive. So we go from something so we go from here that we seldom see anything to here. Now you understand this thing. So why all these values have the same value? Why all these pixels have the same gray value? Because it must be in one of these flat areas of the output of the transformation. So they have to be. I don't know why I don't have it. They have to be, these transformations, they have very flat areas. So all these outputs, they will have the same gray value. And if you want to play with it, you can simply reconstruct this example. Then you take the input is this one. And then you can play with the parameters and contrast enhancement alpha. What is alpha? If you want to understand what alpha is, you have to go to the paper. We will go to the paper in a minute. And then you can play with it and see what happens if you change the alpha. And then this is what we get. And then you can change the alpha and see. So this is the input. This is input to 1. So it is this k minus 1, k minus k equals 0, k equals 1. Yeah. So what is alpha? So you go to the article. Then, so if you go to the article, you see they have the same kind of system representation that I was doing. And then they will explain what K is. So U is the input image, and then they compute this kind of transformation. So it is, they take the image, they multiply by lambda to the K power minimum of this thing, comma 1. So the minimum between 1 and this thing. And what do you think? That is a linear system or a non-linear system? What about this one? This part is linear. You take an image, multiply by something that is linear. So this part is linear, but this part is not linear because the minimum is a non-linear part. Okay, and then here you have alpha. So, and you would have to read the details to understand what is the role of this f function, f star function, and so on. But you see, all algorithms, they have parameters. They have k, they have alpha. And then with the different parameters, you will get different outputs. Okay? And here, I'm sure they have more results. So, and at the end, all these mathematics, they have to be translated into code. So this is pseudocode. So going from this pseudocode to actual code is relatively easy. And then here they have examples. Okay, so, and this is also something that it is very much. So whenever you produce a new algorithm, you have to compare to many other things. So this is the input image, and then you have to compare your algorithm to other algorithms. So this is the output of this algorithm that is referred in the reference 8, the reference 11, and the reference 2. The one without the reference is their algorithm. So this is the one that they propose. And then you play with the different parameters to see what is the result. So I play with alpha equal 2, beta equal 0.8, and then I get this one. And then if I change alpha, I put alpha 16 and beta 0.4, I get this thing. And you can see that playing with the parameters, you can produce many different things. Okay, any questions?